Spatial mapping is important in hydrogeology and will cover several topics in this area. We'll begin with an overview of describing orientations of lines and planes and a general approach to making a map, as well as some skills related to measuring direction and measuring distance. We'll put this together and make a map using a pace and compass technique. We'll also review measuring elevations and using GPS to measure the locations of points. So the first thing we have to be able to do is to describe the orientation of a line. Now you can imagine that a line in space, it has a direction and a high point and a low point. So if we look at a map, or if we look at the line in map view, it's this black line here. So it's shown like that, and this and here would be the high point, and this is the low point. So we draw this as an arrow where the arrow is pointing in the direction that the line is descending. Now in map view we get a line, or get an angle here that is from north to the direction of our line of interest. That's the azimuth of the line. And we generally describe that using the angle from north to the direction of the line. So if we had another line here, the azimuth would be that angle. If we had another line that was here quite close to north, the azimuth is that angle, 340 degrees, say, something like that. So that's going to be the first step that we need to describe the orientation of the line. The next one is the plunge. So let me erase that drawing here. And in order to get the plunge, we need to put a cross-section through our line of interest. And then the cross-section looks like this. The blue line now is the ground surface, and the black line is our line of interest. And the plunge is the angle from the ground surface down to the line of interest, that angle there. So we need these two numbers, two angles, to describe the orientation of a line in space, the azimuth and the plunge. Now, I will generally use the azimuth as the angle from the north to the line of interest, and so it varies from 0 to 360 degrees. Another format that's often used and can be quite convenient is the quadrant notation. So the quadrant notation for describing orientations is shown like so. So this would be a map view, and we have the 4 points of the compass. And let's have a line that looks like this. So this is the direction of plunge shown here with this arrow, and that is the azimuth, and let's say that's 40 degrees. So in quadrant notation, that would be described as north 40 degrees to the east. In azimuth notation, it's just 40 degrees. Another example would be a line like this down into the southeast quadrant. In this case, the line is described with an azimuth angle like so. That could be, say, 150 degrees. But in quadrant notation, we start with either north or south and measure the angle from either the north or south direction over to the line that we're interested in. So this would be described as south 30 degrees to the east. And similarly, if we had a line like so, the azimuth would be that angle. So that would be, say, 300 degrees. And in quadrant notation, that would be described as start with north and then go 60 degrees to the west. Okay, so both of these methods are used to describe the directions of lines. You're welcome to use either one, and you need to understand how both of them work because you'll probably see both. But what I would recommend is that you adopt one or the other and stick with that one just to be consistent. Let me erase this again. This is the 3D look at this picture. Here's the line that we've been working with, and you can see the plunge direction and the azimuth shown in the 3D view, just to give a little better visualization. So when you're going to describe this, I would draw the line on a map and then also give the magnitude of the plunge by the line. Another thing that's important to be able to describe is the orientation of a plane, and we'll use strike and dip to do that. The strike is the angle between north and the line that is formed by the intersection between the plane that we're interested in and a horizontal surface. So if this is the plane we're interested in and this is a horizontal surface, a horizontal plane, then their intersection is marked by that line right there. And the strike direction is the angle from north to this line. We can describe the strike and dip using a symbol like here, like shown here. It's a T-shaped symbol like this, and this long part of the symbol is the strike direction, and the shorter one gives the direction of the dip. The dip angle will be the angle from the horizontal line shown here to the trace of the plane in the dip direction. So the dip direction is measured perpendicular to strike, and the dip magnitude is the angle from this horizontal surface or the horizontal plane down to the plane of interest along the dip direction. So we recognize then that if we describe the orientation of a line, we need the azimuth and the plunge. With a plane, we need the strike and the dip, but we need one more thing. We need to specify the dip direction. And that's because if we give the strike and the dip only, then we could also have a plane. You can imagine that if we had a plane that was in here like this, that was the mirror image of this plane, it would also have a dip of 40 degrees, but it would be dipping in the opposite direction. So when we use a symbol like this, this line here gives us the strike, and this smaller line gives us the dip direction, and then we write the magnitude of the dip generally by the small line. So this symbol that I'm showing over here is a strike and dip symbol, and that angle there is the strike angle. So when you write this, you need to include those three pieces of information: the azimuth of the strike, so a strike angle, a dip magnitude, and a dip direction. Okay, now we want to make a map. This is going to be just a quick overview of what we'll do. We'll look at this sequence of steps in a bit more detail, but I just wanted to go over it to give you an overview at the start. So the first thing we need to do is have our equipment together that will use a compass and perhaps other equipment for measuring angles and distances. And step one will be to identify a starting point, a base point in the map area. That will be someplace that we can identify and come back to, and we'll put that on the map. Then we need to identify a scale, and basically what we want to do when we're making a map is we have a piece of paper that we're working on. We're going to draw the map out in the field, and we want to try to have the area that we're mapping fit on the paper. And so that involves picking a scale so that the size of the region that we're mapping fits on the size of the paper. So we select the scale and we'll draw the scale bar on here. So that distance on our map represents 100 meters out in the field. And we also will put a north arrow. These two things, a scale and a north arrow, should be on any map. Then the mapping process will involve identifying and measuring the locations of points in the map area, plotting the positions of those points on the map. And then generally what's done is to fill in details that are of interest. And we might have let's see, the edge of a roadway that comes through like this, and perhaps a building that is next to this particular point. So we fill in those details, and then we repeat this as necessary, and then we go and check our map so that we are comfortable that it is accurate enough to serve our needs. So in order to make a map, we need to be able to locate points in space. There are several methods for doing this, and they generally trade off the accuracy that they have with the ease or the amount of work that's required to measure the locations. The GPS, this is certainly the easiest method. If you have the appropriate equipment, all you need to do is press a button and the equipment will tell you the location of a point in space. If you don't have the equipment, or if you need something that is a fairly small map, then a pace and compass map can be a bit more accurate than GPS. It's easy and quick to do. If we replace the pacing with a tape, we can get even better accuracy. So a tape and compass. And then if we replace the tape and compass with a transit, that allows us to have a map that's even more accurate still. So it all depends on our needs. We'll measure the location of one point relative to another using two methods. The most straightforward one, and the one we'll probably use the most often, is to measure the azimuth and the distance. So if we start off with a point right here, that's our base point, and we have another point we want to locate, then we measure the azimuth from our base point over to the point of interest, and so we measure that angle with our compass, and we measure this distance using either a pace, a tape, or a transit. And if we know those two things, the azimuth and the distance, then we can locate this point in space unambiguously. Another approach, though, is when we either can't or don't want to measure the distance, then we have an alternative to locate a point using two angular measurements, or two azimuths. So if we know these 2 points here and here, and we've already plotted them on our map, then we're over here at this point and we want to be able to plot that point on the map. So we use the compass and we measure the azimuth from our location over to this point. And so we're essentially measuring that angle. And we also measure the azimuth from the point where we are over to this location. And that would be, if this is north, that's that angle. So we plot those two lines on the map, the lines that go through these 2 points and have the correct azimuth, they intersect at the point where we are. So that allows us to locate this point in space, and we never have to measure this distance for this particular. We always want to be able to check our work. It's easy to make a mistake either by measuring something incorrectly, writing it down incorrectly, or plotting a point incorrectly. So there are a couple of simple things that we can do to check our work. One is to just simply backcite and verify that we've measured the correct angle. So if we start with our base point we measure an angle over here, and we measure that distance. We plot a point here. Then when we go over here and we're at this point, then we can simply take the compass and measure back to the starting base point. That gives us a different angle, and we can measure, it should be at 180 degrees from the angle that we measured originally. So that's just a simple check on the azimuth. Another more involved check would be to go like so. So if we have a base point that's right here, and we go over and do an azimuth and a distance to that point, and we go and do another azimuth and distance to this point, and another azimuth and distance to that point. Now, at this point, we may want to check our work. We've done several azimuths and distances, and so in order to verify that we're on the right track, we can check the location of this point by basically establishing the location relative to 2 points that we've done previously. Now, we have to be able to see these 2 points, but if we can, then we can go and use the 2 azimuth method by shooting a line from the point where we're located back to the point that we can see, and this would be, say, the azimuth through the first point, and then we measure the azimuth to the second point, and we have a line that's got to go through this point, and let's say the azimuth it's through this point here, and this is the angle. So we plot it on the map, and that check says that the point should be there. Well, by this azimuth and pacing method, or azimuth and distance method, we've said that it's here, and so those are different locations, and they're probably different by enough so that we need to sort out which one is correct. So this is an independent way of locating a point, and if we do see that there is a difference, then we need to go and figure out which one is right, and that'll take some additional work. But this is very important because it allows us to identify that there's a problem as we're working, and if we can pick it up as we're working, then we have an opportunity to fix it.